To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. This Lab 6 has at least 2 circuits to be connected together and tested as a single unit. Hence, it is necessary to consider the space allocation of both on a circuit board. The first circuit, to be studied in Part A, is the high-pass filter as highlighted in light blue. Its output will be coupled to the low-pass filter, highlighted in green. The joint circuits perform as a band-pass filter, whose functions are to be tested with a signal simulation circuit that generates a test signal for the band-pass filter. Lastly, to evaluate the performance of the band-pass filter, its output will be processed by a receiver demodulator circuit. In addition, space allocation should also be considered for the connection of the circuit to the DG lent AD2 for measurements. If you have seen the discussion on high-pass filter, you would see a very similar case here. Everything is equivalent, except for the opposite behavior with respect to frequency. Consider a pure sinusoidal signal input to the circuit. When its frequency f changes, the output behavior is determined by the amplitude term as shown. The behavior of the amplitude versus frequency is characterized by two complex numbers z1 and z2, known as the roots of the transfer function, which are determined by the resistances and capacitances of the circuit. Let's take a look at the output amplitude term. Notice that there are the f² terms in the expression for the output amplitude. Hence, the circuit is said to be of the second order type. This is different from the circuits of Lab 5, where only first order of f appears in the expressions of the outputs. This is log-log plot of the magnitude of the amplitude as a function of frequency, known as Bode plot. It shows the output is constant from DC up to certain frequency, around 10 kHz for this particular design, above which, it is steadily attenuated to zero at infinite frequency. This behavior, which involves the blocking and attenuation of signals with high frequencies, but allowing low-frequency signal passing through, is called low-pass filter. An important figure of merit is how efficient the attenuation versus high frequency is. Because of the frequency squared term in the denominator, if the frequency increases by a factor of 10, the output magnitude decreases by a factor of 100. Thus, the higher order a filter is, the more efficient it is in blocking signals of unwanted frequencies. The following shows how to use the circuit simulation app to tailor the circuit, and compare the calculation versus experimental measurements. Turn on Bode plot and root plot. There is a fast Bode plot option for slow computer, and full graphics Bode plot for fast CPU only. Next, select the resistor and capacitor values. Shown are the starting default values, but they can and should be changed for two reasons. First, if the exact components are not available, and you decide to use the closest values available, change the values accordingly. Second, if you have accurate and high-precision digital multimeter to measure the capacitances and resistances, enter the measured values instead of the nominal values written or encoded on the components. It is essential, however, to observe the Bode plot while designing your circuit. Because it will be used in conjunction with a high-pass circuit to make a band-pass filter, try to obtain a Bode plot that is closely resembled to the original design. The app is turned off and on again in order to restart with the original default design. Once the circuit has been built and is ready for testing, click on Signal button. A pop-up window shows the Nyquist 2D plot, which allows one to get a gut feeling where on the frequency scale to look for the resonance and the rapid phase change behavior. Since the frequency control is on the linear scale, it is much more sensitive to locate the resonance peak than the log-log Bode plot. Check for the resonance frequency and output magnitude on the oscilloscope and compare to the calculation. Tune the frequency around the resonance and observe the output behavior. The display output of the EP is multiplied by a factor, shown as the added dB, in order to plot both the input and output on the same scale. For the real circuit test on the oscilloscope, the output signal can be very small for the frequency exceeding the low-pass limit. Observe and compare. The test results for the frequency range around the resonance can quickly determine if the built circuit is close enough to the intended design for the demonstration of signal modulation applications later on. Step response to a square wave input is also a useful check. Select a square wave period that is much longer than the damped oscillatory response of an input step. This response is what caused the spikes observed in the various demonstrations of the use of this filter for communication signals with noises and interferences. As an extra learning note, if you have learned signal analysis, the damped oscillatory behavior is determined by the design of the roots of the transfer function. If an application demands stronger damping, the root positions can be designed for such a result. But there is a trade-off with regard to the response time. Spiky oscillation corresponds to fast response, mute damp behavior corresponds to slow response. Although the following is not necessary for the building and testing of the circuit, this is an extra learning note, to help those who have learned circuit analysis, to have a visual and familiar connection of the roots of a Laplace transform transfer function to the step response behavior. This behavior is found everywhere in nature, around us, not just the circuits of this lab. There are two parameters determining the roots. The first is natural frequency, which is the radius of the roots. Larger radius means higher frequency, or fast oscillation. Smaller radius means lower frequency, or slow response. The second parameter is the damping coefficient, which is the cosine of the root angle with respect to the horizontal axis. The larger the damping coefficient is, the faster the oscillation comes to a stop. When the roots become real and degenerate, the damping is said to be critical. The larger the real root magnitude is, the stronger and slower the damping response becomes. This is known as overcritical damping. This behavior is everywhere, because the mathematics describing the underlying dynamic mechanism is the same, whether it is a mechanical system, like a swinging door, or an electrical system like the circuits in this lab, or in even social and economic behaviors, wherever there is a second-order differential equation involved. How are the roots chosen? This slide is to benefit those who have taken signal analysis filter design. A filter designer can choose as many roots as needed. There are a number of root configurations as shown here. The figures are the 3D plots of the various transfer functions, where the roots appear as the poles, or the mountain peaks, in the plots. The spatial arrangements of the roots are to design different frequency response behaviors, usually the trade-off between the sharpness of the cut-off edge versus the residual ripples of the output magnitude versus frequency in the passband. The circuits of Lab 6 are the simplest possible as each filter has only 2 roots, the minimum number required for a complex root filter. It should be noted that a first-order filter, such as those in Lab 5, can only have a real root. For amusement, one important engineering task is the design of a damper for tall buildings. A tall building tends to oscillate at its natural frequency with a low damping coefficient. A tuned mass damper placed at the top of a building can increase the damping coefficient and reduce the swaying of the building. The video shows the mass damper of building Taiwan 101, which is exposed as tourist attraction, rather than being hidden from view. This photograph shows a representation of this high-pass filter circuit. A difference from the schematic is the power rails. The plus and minus 12-volt supplies are on two separate inner rails. The ground is on the two outer rails. The photograph is intended to have sufficient spatial resolution and color clarity to allow the reading of the component values as shown, which can be used to build the circuit. Steps B2 to B4 are straightforward and similar to those in Part A, or those Lab 5 and Lab 4. Once the measurement connection is set up, the only differences between the steps are the various waveforms and frequencies. The input test signal and a monitor scope channel should be connected to the circuit input, which is the input terminal of the 1 kilo ohm resistor. A second scope channel should be connected to the circuit output, which is pin 6 of the op-amp. In a test of the circuit on its own, all other connections to other circuits as shown in the photograph should be disconnected. The circuit frequency response was measured with 35 sinusoidal inputs. The frequency ranges from half a kHz to 100 kHz. Fine data points were taken near the resonance to study its behavior. The Bode plots are shown on the left, the 3D Nyquist plot is shown on the right. For the Bode magnitude and phase plots, the dots and the solid connecting lines are experimental data, the dashed curves are the model calculations. The model does not include the realistic gain bandwidth of the LM741 op-amp, hence there is some discrepancy at the high frequency end. Also, the calculation uses nominal values of the resistors and capacitors, no adjustment was made to fit the resonance frequency. A square pulse with duration of 1 millisecond, which is several times longer than the oscillatory relaxation time of the circuit, was used to measure the step response. Since the circuit passes DC and low frequencies, the output should have the same square shape as in the input when the signal is DC-like. However, at the abrupt step changes, up or down, the cutoff of high-frequency components results in relaxation oscillatory response as expected from the root properties of the transfer function. A close-up comparison of the experimental step function response, blue trace, versus model calculation at the bottom shows agreement as expected. A 10 microsecond square pulse signal was used to test the impulse response. The oscillatory relaxation is as expected. Assuming infinite op-amp bandwidth, the transfer function can be obtained with the node voltage equations. The solution of the 2x2 system of equations is then obtained. The transfer function shows its second-order nature with respect to the complex frequency S.